We are moving forward with our parsing. So right now in our linguistic structure prediction pipeline, we have seen part of speech tagging, we have seen named entity recognition, we have seen how to build constituency parse tree, and this kind of gave us a nice tree of constituents, which are, we can think about them as phrases. And today we are going to move to another way of getting syntactic structure out of a sentence. But for a second, I do want to go back to the constituency parsing and CKI algorithm. So CKI algorithm we have seen is a bottom-up parser, meaning we start from the words in our sentence and we start combining those words into meaningful phrases, such as, the determiner and a noun make a noun phrase, a verb with a prepositional attachment make up a verb phrase, things like that. So here, for example, we see that she is a mark with a non-terminal noun phrase, and then this noun phrase together with some verb phrase make up the whole sentence. In that sense, it's bottom up. And it's an example of dynamic programming, meaning we have reused parts of the computation. So once we knew that she is marked as a non-terminal noun phrase, then we reuse that information when we have marked the whole sentence with a non-terminal sentence. I should actually say that sentences always going to have at the utmost level of the tree sentence, but the where we have reused the information that she's a noun phrase is when we have combined this noun phrase, the information about that being a noun phrase with this verb phrase to say, okay, this sentence is composed out of a noun phrase and a verb phrase. Here is how more or less this this example looks, how its constituency parse tree looks like. It's not exactly the same because I use the demo for constituency parsing, which is realistic. It doesn't use CKI algorithm. It is using a neural approach to constituency parsing. It doesn't have this silly little grammar that we have developed here. It has something that's more realistic. So you will see small changes like she will first have a part of speech tag personal pronoun before being marked as a noun phrase. So don't let that confuse you because the structure is more or less the same. And I just kind of wanted to show you how something like this would end up looking like a tree, but notice that there are slight differences, and that makes sense that there are differences because this is a toy example. This is a real output of a real constituency parse tree. Okay, so that's about it in terms of the algorithm itself. I do want to mention how do we evaluate constituency parse trees. First of all, we are going to have a tree bank, and remember we have talked about tree banks last time. This is a data set where you have sentences that are manually labeled by experts, usually linguists, with syntactic structure in a given formalism. For example, constituency formalism and building constituents parse tree. So you have a labeled data set. And what you want to know now that you have developed an algorithm for constituency parse tree is how good your constituents are. And to do that, you are going to check how much the constituents in your hypothesis parse tree, the one you have generated, look like the constituents in a head labeled reference parse. And we'll say that the constituent in a hypothesis parse of a sentence S is labeled correct if there is a constituent in the reference parse with the same starting point, ending point, and non-terminal symbol. Basically saying, okay, if you say that this phrase in this sentence, if this substring is retrieved to be a phrase under your constituency parse tree and it's labeled, let's say, as a noun phrase, you are checking, is that really a constituent in the reference human authored parse tree, and is it labeled also as the noun phrase in this specific example? So yeah, we will have labeled recall being number of correct constituents in hypothesis parse of the sentence over the total number of constituents in a reference parse precision, again, out of those that you have labeled, out of all of the correct constituents in your hypothesis parse of the sentence. Um, uh, Sorry, why am I confused by this? Let me just go over this on my own just for a second because this. Uh-huh. So, sorry, I was confused for a moment. So what this precision is calculating out of all the constituents we have retrieved and labeled in certain way with our automatic constituency parse tree, how many of them are actually correct in terms of being both constituents and being labeled properly. And once you have the recall and precision, you are just going to calculate F1 score as always, because we do care about both the recall and precision. All right, so that's basically it about more or less it about constituency parse tree. Again, for all of these things we are talking about right now, you would use spaCy most likely to get the automatic annotations. So here I just provided a screenshot of the code you need to use certain constituency parse tree implemented in spaCy. And as you can see, it's quite simple. Once you load the spaCy model, you would add to your NLP pipeline certain constituency parse here, tree parser. Here, the constituency parser we are using is implemented in this paper. Again, constituency parsing with a self-attentive encoder, and then you can just once you call the pipeline on your given text, you will get all the things that are included in the pipeline. And since you included constituency parsing, it will be part of the output. So here you can see how easy you can get the constituency part out of the sentence using spaCy. Now, I want to emphasize again, the same way I have emphasized when we learn hidden Markov model for part-of-speech tagging and named entity recognition. I have introduced for hidden Markov model, and I introduced CKY algorithm to you to learn about these algorithms, but these are not state-of-the-art algorithms. So when you use spaCy, you are not getting the outputs of a hidden Markov model for part-of-speech tagging and named entity recognition, and you are not getting CKY algorithms output for constituency parse tree. Mostly these models that are implemented in the spaCy will also be neural models. And we don't have time to cover now how we would go about using neural models, but more or less you know all the machinery needed to use a neural model for any of these things that we are talking about this week and the last week. It's just a matter of how you do the prediction. And that's basically it. But I will not go into details of that, and feel free to check the paper if you want to know. All right, so that's it about constituency parse tree. Are there any questions and about the constituency parsing? And actually, I will just step out for a second to grab water. But you think about your questions, and I'll come back in a second. All right, I'm back. Sorry about that. I simply cannot teach without water. Any questions that I missed? Okay. So then we are going to move to dependency parsing. Okay, so I remember when I said there are different grammar formalism, and when I told you linguists generally do not have a single theory that rules everything, and we just follow that theory. So for syntactic parsing, for finding the syntactic structure of a sentence, linguists have different formalism, grammar formalism that we can follow. So far, we have talked about constituency parsing that follows constituency formalism, where we think about language in terms of these phrases and how we compose phrases to get grammatical sentences. Today, we are going to learn about a different formalism, and that's going to be dependency formalism. And when you follow dependency grammar formalism to do, to find the syntactic structure of a sentence, then we have dependency parsing. Okay, so the distinctive feature of dependency formalism relative to constituency formalism is that we are thinking about the syntactic structure of a sentence in terms of directed binary grammatical relationships between two words in a sentence. So let me illustrate this. Here we have a sentence, the tabby cat scratched the couch. The main verb that we will sometimes refer to as a predicate of this sentence is scratched. And we have in the dependency grammar formalism two arcs going from this word scratched, from scratch to cat and from scratch to couch. Now I will introduce some important terminology. Here, the word scratched is in this arc relationship, it's called head. Head is the word from which the arc relationship is going from. So here we have our head, and the word that the arc is pointing to, that word is called dependent. And informally, you can think about when we have head and dependent, head is usually the central organizing word, and dependent is something like a modifier or, in this case, a subject or object of the verb. So for maybe when we move forward, I will stop again and show you again bring this notion of the organizing word. So in dependency formalism, we do not only have these arcs that tells us, okay, these two pairs of words are related in some way, but we also have a label for that relationship. In this specific arc over here, the relationship is subject. And the way you can read this in a very formal way is that we have a head word scratched, and dependent word cat is the subject in the subject relationship with the head word. And similarly here we have object relationships. So dependency arcs are labeled with these grammatical relationships such as subject, objects, noun, modifier, determiner, and so on. And the label describes what grammatical function the dependent plays with respect to the head. Here we have all the arcs for this sentence, not labeled yet. And importantly, every word in a sentence should be covered by the tree. So in every one of them, there is some kind of arc coming to, except the root will be a special one, and usually root node explicitly marks the root of the tree, and very almost always is going to be the main verb, or as we sometimes call it, predicate of the sentence. And here you now have all the relationship between pairs of words for which we do have a grammatical relationship being labeled. So, when I said, okay, head word is often this organizing word, let's maybe come back to that. So here you see we have a few determiner relationships. And here determiner is the determiner of the noun, which is exactly what I meant, like head word is a noun and then determiner slightly modifies that noun. Similarly here you have a modifier tabby. It is dependent, it modifies the main verb in this relationship, which is the cat. Okay, and this is an example of a full dependency parse tree, and it's always going to look like this, where you have these words will just be placed horizontally, unlike in the constituency parse tree where they are at the bottom, of the each branch, so it can be a little bit tilted, right? Here, they're always going to be represented horizontally with these arcs above them that are labeled. Okay, any question about dependency parse trees so far? Is it clear what the head is, what the dependent is, that we do have arcs between two words, only two words, and that these are labeled? Okay, hopefully, yes. Um, all right, so let me take a moment to contrast the dependency parse tree with the constituency parse tree. So on the left side, we have a visualization of a dependency parse tree, but please remember that this is never how we represent dependency parse tree. This is just for the sake of this illustration. We are always going to have dependency parse tree being presented like this. This visualization of a dependency parse tree serves only for the purposes of this single slide. What I want to show you here is first that no node corresponds to phrasal constituents, such as noun phrases or verb phrases, right? We have the pairs of words, and we are saying, hey, are you in a grammatical relationship? And if so, how does the dependent grammatically relies on the head word? So if you need later, for example, you have a big corpus and someone tells you, hey, can you find all the actual grammatical phrases for some reason in this corpus? You would use a constituency parse because it's easier to retrieve the phrases out of it. So here you just go and do, here we have, let's say, a noun phrase, which is the words that are under this noun phrase are the morning flight to Denver, or prepositional phrase through Denver, and so on. It's way easier to extract phrases out of constituency parse tree than it is from the dependency parse tree. Nice property of the dependency parse tree is that the arguments to the word are directly linked to it. So here we have a sentence that says the sentence is, I prefer the morning flight to Denver. And in dependency parse tree, prefer and flight will be one arc away from each other. They are immediately connected. However, if we look at where they are, these words in the constituency parse tree, we see that prefer is over here, while flight is all over here. So if you want to retrieve, let's say, verb object relationship from the constituency parse tree, it might require more work than if you just use dependency parse tree, where these things are just an arc away from each other. So that's a nice property of dependency parse tree. Okay, and what is not illustrated here, because of this property where things that are grammatically connected to each other are going to be close in the dependency parse tree, that makes dependency parse tree nicer for languages where we have a more free word order, where words that are super connected to each other grammatically can be completely far away from each other in a sentence. I keep bringing up the example of German, where a verb can be composed of two parts, one of which will appear in the second position of the sentence, and the second part of the verb is going to appear all the way at the end. That's how grammar works in German, and this will make it hard to find this connection in a constituency parse tree. Well, it's super, super easy to get it in the dependency parse tree. Okay, so two different formalisms, both of them have advantages, and it really depends what you want, what are you looking to do with these syntactic structures. Questions? Okay, seems like we are all ready for the Thanksgiving break. Almost there. Okay, so I will first now define the dependency formalism, and then we are going to see a first algorithm for dependency parsing. Um, all right, so to define dependency formalism a bit more formally, we would say that we have a directed graph composed, of course, as always, of vertices, which are words, but words, it's a more broader sense of set of words. It can be also punctuations and sometimes even stem and affixes. And we have also a set of labeled arcs, which are order pairs of vertices, right, with labels. However, this graph has certain conditions. Uh, uh, it needs to follow the following, I believe, three constraints. First, there is going to be a single designated root node that has no incoming arcs, so nothing comes into the root node. And with the exception of the root node, each vertex, so each word has exactly one incoming arc, okay? Not more than one. So a word can send multiple arcs from it, but only a single arc can be directed into the word. And there is a unique path from the root node to each vertex in our set of vertices. So what does this mean for dependency parsing? This means that each word has a single head. This comes from the fact that each word, each vertex has only one incoming arc. Okay, so it has only a single head. The dependency structure is connected. This is comes from the third property. And there is a single root node from which one can follow a unique directed path to each of the words in the sentence, which also comes from the third one. Third and the first one. Okay, so these are the properties that this kind of graph needs to satisfy. Okay, so we had tree banks for constituency parts tree. We mentioned pen tree bank, and I have also mentioned that even within a single grammar formalism, remember part of speech tagging, you can have different tag set, right? We had pen tree bank tag set, but we had also universal dependency tag set for part of speech tags. And this is where universal dependencies are relevant again. So for dependency parsing, there are different, I don't know, I'm missing the word, different annotations of the dependencies that people have developed. But one that's super popular is universal dependencies. And UD is an open community effort with a goal to annotate dependencies across more than 100 languages. And it provides an inventory of 37 dependency relations and over 200 tree banks. It is one of the resources in natural language processing, which covers the most languages, which should be a little bit concerning given that it's only slightly above 100 languages, and from a trace lessons you have learned that there are over 7,000 languages in the world. So even though it's a resource that tries to cover a lot of languages, it still misses a lot of languages, which kind of says more about the state of the art for how NLP works for all of these languages we have in the world. But nevertheless, it is quite substantial in what it tries to do. And in their own words, their general philosophy is to provide a universal inventory of categories and guidelines to facilitate consistent annotation of similar constructions across languages, while allowing language-specific extensions when necessary. And this is another nice property of UD. So if you have these universal guidelines about how this should be annotated, then it can enable, for example, cross-lingual transfer, where you can try to align For example, oh, what is the verb in this sentence in this language with what is the gonna be the verb in another language. So it is quite nice in that sense. And yeah, people are continuously developing the dependency formalism for their languages. For example, Matre had contributed largely to developing first dependency formalism following the UD for Gujarati. Okay, so universal dependence is extremely important. Not surprising that it has won the test of time award in the last year ACL, which is the top conference for NLP. Okay, so just to kind of take a moment to step back and see where we are, we have introduced the dependency formalism, another formalism for defining syntactic structure over a sentence. Previously, syntactic structure was done by finding constituents, those phrases that on their own make kind of sense, and putting them into a tree bottom up. And here we are looking at the binary relationships between two words and checking whether they are grammatically related and what's their grammatical relationship, and then putting all of that into a tree. And then when we need to decide whether the two words are grammatically related and in which way, we will go, for example, to universal dependencies schema and check under the rules of universal dependency schema, what do the creators say we should, what kind of rules we are going to use to say that something should be connected or not. Okay, so now we are going to see how we can use this information. So we have this tree bank, for example, in various languages. How do we use this to develop a dependency parser that can take any sentence and then produce one of these dependency parse trees for you? Okay, questions? All right, so we are going to see now one algorithm for dependency parsing. I'm going to use Professor Vivek's slides because they have very nice animations. And I will be asking you to participate in when we start looking through the examples. So try to pay attention, and then we will work one example together. Okay, so in transition-based parsing, first of all, transition-based parsing is just one of the possible ways of approaching dependency parsing. So don't think of this as the only way, but this is one way that we are going to learn. And it is a simple, greedy, discriminative parser that executes a sequence of actions that update the parse state. Now, parse state, I will define parse state and I will define a few things, and then we are going to use all of that through an example. So this is now just bringing you a few definitions before we do anything else. Parse state is going to consist of three things: buffer, stack, and set of actions. A buffer will initially consist of all the input words we have. The stack will be a structure whose top two elements are going to represent the next words that can be connected with the dependency edge. And then a set of all the actions are a set of all dependency edges that have been created so far. So this is our parse state that's going to be iteratively changed. Okay, I don't know why. Okay. This is a little bit cut. Oh, no. Sorry, guys. Let me just try to see, can I... Okay, this is better, right? Okay, in terms of the actions, we are going to produce actions that are going to change this parse state and give us another parse state. That's what the actions are going to do. So in other words, if the parse states consist of a stack, buffer, and set of actions, by doing another action and changing the parse state, that means we are getting a new set of buffer, stack, and actions. And if you know compilers, then you will be happy to learn that this behaves like shift and reduce in the shift reduce parser. And basically shift is going to move a word from the buffer to the stack, and we will have different kinds of reduce action that we're going to produce dependency edges. This is all very high level. We are going to see an example that will make this all more concrete. Importantly, there are different kinds of transition systems whose behavior is defined by the set of actions. We are going to use arc standard transition system, which consists only of 3 actions, which are shift, left arc, and right arc. Okay? All right, so I'm going to go over these 3 operations that we have with the transition-based dependency parser in general, how they work, and then we are going to see concrete examples that should hopefully make it extra clear on how these things work and how we are building the dependency parse tree using this algorithm. So just a reminder, we are going to have first of all, we have a parse state that consists of a stack, here denoted with sigma. We have a buffer, and we have a denoting a set of dependency arcs that are created so far. This is our parse state. So basically what we are seeing on this slide is a parse state. And I said we are going to have 3 actions that are going to change this parse state. And by changing parse state, what then this means is we are going to make actions that are going to change the stack, buffer, and the set of actions. By set of actions, I should say set of dependency relations we have accumulated so far. All right, so shift action is going to look at our buffer, and it's going to take the first element in the buffer, whatever is at the top of the buffer, and it's going to place it at the end of the stack. So it's basically shifting from buffer to the stack, this element that's at the beginning of the buffer. So once again, here we have wi being the first word in the buffer, and we are placing that word at the top of the stack. So if the buffer is to the right of the stack, this visualization of shifting hopefully makes sense. Now, there is this notation above. It's not super important for you to know this notation. I will walk you through. If you imagine that there is this pipe, then that is after the first element in the buffer, then we have our stack. We have the W1 being the first word in the buffer, and then pipe, and then the rest of the buffer. When we do shift, then we have our stack. We have word W, excuse me, I should go here. We have our stack, and we have at the end of the stack W, and then rest of the buffer and the dependency actions. I don't think this is super important, so if that notation is confusing, you can also ignore it. Okay, there is a question. Are buffer or stack sorted based on next word to process? So yes, there is an order here. You start your buffer will be you will put your words in your sentence in a sequence they appeared. So the first word in your sentence will be the first word in the buffer, and so on. And initially, your stack will consist only of a special root node, and there will be nothing else. Or if you can even imagine it, a stack being empty. And your set of dependency relations you have created at the beginning will, of course, be empty because you haven't created any. So you will have empty stack, buffer, which is a list of words in an order they appear in a sentence, and then empty set of dependency relations so far. Okay, so then our left arc operation is going to look at the top 2 elements of our stack, and it's going to make a decision of whether the word that's the last word in the stack can be ahead of the second to last word wi. So in other words, you are making a decision of whether you can place an arc relationship from wj to wi. That's the decision we are making with the left arc operation. So if you pay attention that here we have w1 and wi and wj. For example, this can be wi can be a word that's modifying a noun. So maybe this is, as we had before, the cat. And if you have the cat, then you know, okay, the is according to universal dependencies rules, if we are experts and understand them, we would determine if we are doing these annotations manually ourselves that yes, W is then the head of WI, and that there is determiner relationship between them. And if we do that, we have placed the left arc because it's going from WJ to WI, so to the left. And we are going to then save the WJ in our stack. It's going to be still there, but WI is going to disappear. So basically WI, WJ is just replaced with WJ. And we are going to record that relationship in our set of dependency relationships. Notice here how the order is WJ and then WI. This is because we are recording that there is a certain relationship, such as determiner, from head word to the dependent word. So this is always going to be in a first position, the head word, and then the second word is going to be the dependent word. So it's extremely important to pay attention to that detail, that you don't swap the order, because then it would look like that the arc is going to the right, which is not true. Oh no, sorry about that. Can someone tell me why are we still keeping WJ? Given the three properties of the dependency parse tree that we have set when I talked about how to formally define the dependency formalism. We had three properties of the graph, and then one of them comes into play here.
Can you hear me?
Yes, I can.
Okay, great. So it is because each word can receive only one edge, one arc, but it can send arcs to multiple words.
Perfect. That's exactly the reason. Yeah. Basically, WJ can still be a head to another word, right? So it can still serve in the left arc operation, but WI had received a head right now, and it can no longer serve as anyone's dependent, and therefore it's disappeared. Okay, so we know in dependency parse tree that I've seen before, we don't just have left arcs, right? There are left arcs, and we've seen right arcs as well. So unsurprisingly, here we have a right arc operation operating quite similarly. We have at the top of our stack WI, WJ, and now we are experts in dependency parsing. We have universal dependency schema guidelines, and we are deciding whether we are going to connect WI and WJ with the right arc operation, which means that we need to decide whether this current word WI can serve as the head and WJ as its dependent. For example, we had verb, and then object very often comes after the verb. So WI here could be a verb, and then WJ could be an object, and we could place object relationship between them. And similarly, like with the left arc, here we are going to keep WI at the top of our stack, because it can still serve as someone else's head, right? And WJ here is the dependent, and it no longer can be anyone's dependent. And in the record of our dependency arcs we have created so far, we are recording now in the order WI, WJ, because remember here, always the first one is the head word and the second one is the dependent word. Okay, so these are our three operations, quite simple. And we are going to see how this does this work on an example before we move forward. All right, so when we start transition-based dependency parsing, our parse state will look as follows. It's going to have this special root in the stack. In our buffer, we are going to put the words in the sequence that they appear in our sentence. So we have the sentence, the tabby cat scratched the couch, and we are going to place them in an order they appear in the sentence. And our dependencies so far are going to be empty because we don't have any dependencies yet. Now, I will immediately tell you that, okay, I don't know, let me do this. Okay, hopefully that's visible enough. Okay, so we need to have two words at the top of our stack, so we are always going to start by shifting twice, right? Once and then second time, right? Because we do need two words at the top of our stack. Now we have the tabby, and I don't know whether this is intuitive to you, but these two words are not in a grammatical relationship, right? Like there is something missing, some noun that connects them all. On their own, they are not grammatically related. And again, decisions of whether something is grammatically connected or not are slightly hard to determine for you and me because we are not experts who have read the guidelines and who know this super well. So some things will be intuitive, some won't. Maybe this is an example where why these two things are not grammatically connected is not super clear to you, but you will need to trust me that they are not grammatically related, and therefore we wouldn't put either left or right arc, and what is left is to shift, right? So we shift, and now we have the tabby cat at the top of our stack. And we need to make a decision of producing a shift or left arc or right arc operation. Does anyone want to try to see what kind of operation you would apply at this step of transition-based dependency parsing? Left arc, that's right. Elham, do you want to walk us through why?
Because cat can be the head, and then the and tabby can be separately the receivers.
Okay, but pay attention, you mentioned both the and tabby right now. So remember, it's okay if you forgot, but do you remember how many words can we take from the stack in a given moment?
Yeah, just to the top two.
Okay,
Yeah.
so can you specify which two in this?
Tabby and cat, I guess.
Mhm. Okay,
Yeah.
yes. So the tabby and cat, and you're right that cat can be the head, and the tabby can be dependent because tabby is modifying the noun cat. So here we would indeed put this left arc operation, and the specific label for this kind of relationship between and a modifier and a noun is called a mod or adjectival modifier. So you can, here is a description from the dependency parser, excuse me, from universal dependencies. And this is what I mean by you need to know everything about universal dependencies to be able to do this decision. Here it is slightly intuitive, but knowing that this is actually a mod is something that comes from universal dependencies, and your annotators are experts who read all of that, and they're likely linguists, and they know which decisions to make. there is a question. How does the algorithm determine that the tabby aren't related in step two? Is it from universal dependencies? Yes, exactly. This comes from a universal dependencies. Guidelines will tell us do not connect these two words. There isn't a relationship in our set of relationship that the describes them. So maybe if I go and see, can I find all the relationship in universal dependencies? Okay, so you see here UD annotation guidelines. You as an annotator would read all these guidelines. And let me see, can we find English here? You can see how many languages there are as well. Here, let me see, can I find tags? These are part of speech tags. I'm looking for, no, I'm looking for the set of relationship. I would like to show you. Give me just a moment. Syntactic relationships. Okay, so here are the set of relationships between two words according to universal dependencies. And Ryan, what would annotator needs to do if they are annotating and doing this manually is learn about all of these relationships as they are defined, and then they would mentally come to the conclusion that the and tabby, there simply isn't a relationship here that would describe the grammatical relationship between these two words, and then they would decide to do shift operation. Okay, so we followed Enham's suggestion, and we ended up with the uh, left arc operation. Let me just check something. Okay. Okay, so this is just illustrating what we have just described. We have taken cat and tabby. We decided this is a mod operation. And now, importantly, we have recorded this operation, right? And what is going to then be placed back at the stack?
It will be the head, which is cat.
That's right. So cat is gonna be moved back to the stack because it can serve as the head again. Oh, now imagine there is a the and cat, and then I would like you to tell me which operation can we do next. I'm not showing that cat is appearing here because in the same slide the operation will be shown. So if we had the and cat at the top of the stack, what would be our next operation?
Again, left arc.
Left arc again, because do you have idea, Elham, which relationship?
It is determiner. Yeah,
Yeah,
but I
exactly.
don't know how it's called.
Yeah, it's determiner. So the is the determiner of the noun, and it's going to actually be called determiner in the UD. So again, we have taken the two words, the and cat, that were at the top of our stack, and we have, according to the our guidelines, determined that yes, there is determiner relationship between them, and therefore we are going to record determiner in our set of the dependencies. And we are going to place back cat at the top of our stack because it can still serve as a head of something. Okay, so now we have just a cat, so we need to shift because we need two words. We have cat and scratched. Thoughts on which relationship it's gonna happen here?
I think it must be subject.
Subject. So cat is the subject of scratched, right? And is this going to, Ryan, you say it's a right arc? If it was a right arc, that would mean that cat is then the head word. Um, what do we think about that? What do we think that cat or scratch is going to be the head word here?
Scratched must be the head, and it will be a left arc because the top of the tree was the verb, and it was going from verb to subject
Yeah.
and object.
Yeah, exactly. I think this might be a slightly, let me just show the illustrations, slightly less clear cut. And one of these examples where a little bit of, domain knowledge would help. But word will always be the head word in a pair of the words. So in this relationship, subject relationship, the subject is always going to be dependent of the subject relationship, but I do understand that's a little bit domain knowledge. So now I understand why someone would think this is a right arc as well, but it is left arc. And we are going to then record subject and scratched. And again, what goes at the top of our stack?
Scratched.
Yes, scratch goes at the top of our stack. Again, we need to do shift because we are missing the words. Now we have scratched and the. Again, I don't know whether this is intuitive, but this is grammatically not related. And now we have scratch the couch. So again, I think we by now all know what's going to happen, but I would love to hear someone else than me say it.
Should I say? Okay.
Yeah. Or Piyush, do you want to go ahead? We are gonna try to participate.
I I think it can be the left arc, and couch will be the head,
Exactly.
and the tag would be the determinant.
Perfect. So we again take the two top words, which are the couch. Couch is the head word. The is modifying it using the determinant relationship. We are going to record that relationship in our set of dependencies, and we are going to put back our head into the, at the top of the stack. And then finally, we have scratched and couch. And this is going to be an example of the right arc operation, where scratched is going to be the head. Again, verb is almost always going to be a head, and the couch is going to be the dependent in the object relationship. Okay. And then once okay, let me just, okay. Ooh, sorry, guys. I'm a little bit lost in how to switch between slides. Finally, when we have this root, then and the buffer is empty, then we know that the root is going to be the head, right? Nothing goes into the root, and that's it. We are going to stop when the stack contains only root and the buffer is empty, which has happened right now. And now we have all these relationships, and Vivek didn't have an illustration of that, but now that you have all these dependencies, what you do is you just visualize them, right? You put arc between from head to the dependent, and you label it with a relationship that you have determined exists between these two words. As I said, this indeed will always look like horizontally words with arcs with the labels top of them. This is a demo by Stanford Core NLP, which is quite useful if you want to check dependencies and constituency, parse trees, and part of speech tag, NER. It's a great demo to get the linguistic structure prediction on top of a sentence. And again, you can see here something that looks quite similar to what we had come up with through this exercise. Okay, so let me just quickly go over, this was an example. I will just quickly go over the algorithm in a more abstract way. So as an input, we are going to have a tokenized sentence. Initially, our parse tree will consist of a stack that contains only the root of the buffer that contains all the words in the sequence they appeared in the sentence, and our set of dependency relations is going to be empty. And then we are going to go repeat certain set of actions while we don't have the root in our stack being the only thing we have in stack and buffer being empty. What we are going to repeat is these actions. Actions can be either shift or left arc or right arc. And typically, when we develop actual models for this, the model is trained to predict the action it needs to do. So there are 3 classes, and it predicts the class which determines which action to do, right? So class 0 can be shift, class 1 can be left arc, and class 2 can be right arc. Importantly to know, this is a greedy algorithm. Once you made a decision about what to connect and how to label it, and once a word becomes a dependent, you can no longer fix that. So it doesn't have an opportunity that for us to revisit the decisions we have made before. Okay, once we made this action, what we do is apply the action to the state, which means we have changed our stack buffer and the set of dependencies relationships we have identified so far. And that's it. It's kind of simple, right? But it's pretty effective and quite popular for modeling to this date. Okay, so now let's just see a few modeling decisions here. And unlike for constituency parse 3, where I just showed you a pre-neural algorithm, here I'm going to talk about various possibilities, both pre-neural and neural, but maybe not in all the details. Okay, so the modeling that we need to do is given our current parse state, meaning given our current stack, buffer, and dependency relationships, we need to predict which action to take, to shift to left arc or right arc. Okay, so as I said, this is a multi-class classifier. We have 3 classes. So given some features, you can try to make the prediction of these classes. And if we were doing this, in general, pre-neural or once neural approaches have become popular, it is clear that information you are working with is what is at top of our stack. We have, what are the top 2 words? What are the features of those two top words, right? To determine whether they are related by one being head of and the other dependent. When we were deciding whether the and cat are in a relationship, I think we have all used information that the is an determiner in general. That's it's part of speech tag. And we have used information that cat is a noun, right? So, and knowing these 2 pieces of information, we have determined, well, then cat is the head and the is the dependent, and they are in this relationship. So if you were building a model for this, you can introduce all these features into the model for it to have a chance to also do something similar to what you have done. Okay, so let me just see whether I'm missing anything here. So again, words in the stack and the buffer, properties of those things like part of speech tags. We need to consider the position that, we could determine whether it's left or right arc only based on whether cat is the first or the second word in the top of the stack. And if the model is so doing this, then information about previously generated children of the words on the stack. Okay, I won't go into that point. All right, so I'm thinking whether I should ask you. Okay, let's say we are building a classifier that basically takes the 2 words that are at the stack and then decides whether to label them with the class 0, 1, or 2, which are shift, left arc, or right arc, right? In pre-neural world, we have said that useful features are then the part of speech tags and things like that. So this could be our features. In the pre-neural world, in the post, after neural networks have become important tools in our tool set, how would you approach this? Like, what could you do? I think we have few options here.
Is it maybe adding probabilities to everything?
You can have logistic regression with manual features, and it's still probabilistic model. Yeah, probabilistic or neural are not orthogonal concepts. Ryan?
Yeah, I just had a quick question, kind of regarding that.
Yeah.
So if we were doing like a neural approach, we would do subword tokenizer, right? Like we'd kind of run one of those. And so,
You don't need to use, again, subword tokenization is a choice. You're not, it's a choice unless you are using a pre-trained language model where you are stuck with a subword tokenization. So you are maybe using a subword tokenizer, but not necessarily.
okay, maybe that would help in this situation because it would be easier to determine like a verb. Because like if it had like ing as a suffix, you could say running as a verb, and then maybe it would be able to learn relations better that way. I'm not too sure, but I don't know.
Potentially and generally, subword tokenization helps. So some of these parsers have also been built in the era around 2016, 2017, 18, when maybe subword tokenization has only started to appear. So you will see a lot of these dependency parsers still working with full words. But the choice of subword tokenization is again not the what makes neural networks, right? So have we ever had with our neural approaches any manually designed features, for example? That's a question for you all.
I don't think so. No, right?
No, right? So if I said, okay, we can use these features such as part of speech tags or things like that. What did we do with neural approach, and what kind of assumptions we made about the representations of our words? First of all, what were the representations of our words, and what kind of assumptions we made that makes the explicitly adding part of speech tag to our neural approaches unnecessary? Let's start with what were the ways that we were representing words or tokens.
With vectorized embeddings.
Yes, right. So we had embeddings for our words. So for cat and scratch here, we can have an embedding, right? And we know that the meaning of these things is such that the vectors that have similar words that have similar meanings will have vectors that are close to each other. And what I meant, and I guess my question is too vague about like why didn't we see a lot of you know explicit features about grammatical roles or other linguistic, properties of our sentence in these neural approaches is because we are assuming that these vector representations are already themselves capturing a lot of these useful information. So instead of giving an explicitly part of speech tag, we are assuming that the word embedding of the word cat is somehow implicitly in these numbers capturing information that this is a noun. And when we have a vector of the determiner, we are assuming that somehow in this vector, information about this being a determiner is captured. This is the assumptions we are making when we are using neural approaches without manual features. So in our neural approach to determining whether the top two words are in a relationship or not is to take a word embedding of the first one, take the embedding of the second one, for example, concatenate them, and then just classify the resulting vectors with either feed-forward neural network that can have one or multiple layers, or we can use a recurrent neural network, place one vector, then the next vector, then make a prediction atop of the second representation. We could also do a total overkill and use a transformer. Nothing stops us, where we will have self-attention, right? And we can have a special classifier token in front of them, and so on. The point is that with neural approaches, we would take input embeddings, and then whatever is our favorite, neural approach, we would just, get the nonlinear representations of those tokens that we would combine to get a single vector and then classify this vector into three classes for shift, left arc, and right arc. Elham, I don't know whether that's a question or a confirmation.
Yes, I'm sorry. Yeah.
Okay.
So the problem is that, like, the problem that I think of is that when we want to classify them in a neural network, the two consecutive words can have a relationship or not based on the rest of the sentence. Like, it is not only about them. Like, in this sentence, if it was the Tubby scratched the couch, then there was the modifier of Tubby, and it was then they had this relationship. But in the current sentence, they don't. Isn't it confusing?
If we were just the okay. Here we have this transition-based dependency parser, and we are following this dependency parser idea exactly as it is, set out with the algorithm. We are just looking at how we can make those predictions that we have been making with a modeling approach, right? And the decisions we have been making were based only on looking at these two words, right? Like when I asked you what to do in the next step, you just took the last two words in your stack and you made a decision, right? It wasn't contextualized with respect to what else is there in the buffer or what happens in the what is already recorded in the dependency, in the set of dependencies that we have seen. So what you're mentioning is limitation of the algorithm in general, not about the specific way we are modeling it with a neural approach.
So the reason why I didn't ask it earlier, because I didn't know how the inference works in this algorithm. But in neural networks, I don't see if we train the classifier to assign a label just based on the two given words, how it can work there. Like how it faces with that ambiguity. I don't know about the inference algorithm in this setting.
Well, the inference algorithm is just look at your back at your, so here, this is the set of dependencies we ended up with these over here. This is the set of dependencies we have created, okay? That's it. And now it's so very simple. You just take these dependencies one by one and you put the arc in the way that the dependency is, defined. So for example, the first dependency tells you make an arc from cat to tabby and label it with a mod. Then take this second dependency and put an arc from cat to the and label it with determiner, right? So once you have made all these predictions, right?
Yeah.
You're just using that information. This is basically the parse tree. It's just written as a sequence of relationships that you can then visualize as a dependency parser.
Yeah, but these relationships, we knew that, for instance, they and tabby did not have a relationship because we had the label. But about unseen data, it still does the same. But I think
Well, you need to simply trust machine learning, right? This is not different from any other case of machine learning you have seen in so far, right? We will have training data. This is going to be a supervised algorithm. So classifications of two words that the neural model is going to do based on the word embeddings is going to be based on seeing some examples of that in the training examples. So it might not necessarily have seen cat and tabby, but it might have seen cat and tuxedo or whatever other type of cat there is. And maybe it kind of concludes, as many times we are hoping our algorithms will, that, okay, this is likely a modifier relationship. And this is where these word embeddings actually come into play very nicely, because in your word embedding space, tabby, tuxedo, Persian, and all of the other types of cat might all be close to each other in the vector space. So although if you haven't seen a particular breed of a cat in the training data, at the test data, the model can use the information that these appear very close in the embedding space to then determine that this should probably be, again, left arc operation. Yeah. So maybe I didn't emphasize we'll have training data and that these decisions are going to be learned through the training data.
Okay,
Is
thank you.
that clear? Okay, yeah, cool. All righty, let me see where we stopped. Okay, so note that in earlier neural dependency parser, sometimes people also trained embeddings for part of speech tags and introduced these additional embeddings into their system. But have in mind that a lot of those approaches have been replaced with neural networks that work only with word embeddings, and that any kind of additional operations, additional manual information is unnecessary. That was very, very, very popular in 2016 to 2018 in NLP. A lot of what we have done there is to try to remove any kind of manually designed features into a system to have what we would say like fully end-to-end neural models. Yeah, but again, what is important here to remember that with the transition-based dependency parser, what you are doing is a model that makes decisions, three types of decisions, which are always set fixed three types of decisions. So this is in your head, you should immediately think, this is a classification, multi-class classification into one of three possible classes. And the decision depends only on the top two words in the stack. So as long as you have features of those two top words, you can build a classifier at top of it. And in this course, we have heavily focused on neural approaches all the way back from feed-forward neural networks to RNNs to transformers. Here, I think the simplest type of neural network we have learned about, where we just have word embeddings, concatenate them, build a few layers of feed for a neural network, classify into one of three classes, is a completely reasonable approach to think of. Okay, so let me see what else Vivek has over here. Okay, this is just a visualization of a neural network, and that's it. Okay, so I want to finish with evaluation. So our dependency parsing consisted of basically two main decisions to be made. And which also brings me back to our neural approach. I said there are three types of classes: shift, left arc, and right arc. But now I notice that that's incomplete. That's only predicting the type of the action we are going to make. If we had only did that, what is missing? If I'm only deciding shift, left arc or right arc, what will I get? What will my dependency parse tree miss? No relationships. I mean, by relationships you mean labeled relationships, right? Like this just told me these two words are in this grammatical relationship, but it didn't tell me which kind of relationship. So your label set is actually three times the number of actually shift plus 2 times the type of the relationship. So for each of the left and right arcs, we can have all of the possible dependency labels as an option. So it's a way bigger multi-class problem than just 3 classes. Okay, now into the evaluation. You will see why I remember this. We have 2 things that we need to do with dependency parsing. One is to decide whether 2 words are in a grammatical relationship and whether one is head of and the other is dependent, which would give us unlabeled dependency parse tree. And then the second problem we are doing is labeling all of these arcs that we are creating, right? And this is why we have two scores in when we are evaluating dependency parse tree. One is the labeled attachment score, and the other one is unlabeled attachment score. Oh no. Sorry, guys. You see how this is cut over here? So if you are confused, why am I confused with my slides? It's because I'm trying to make them visible, but it doesn't really work. So we'll do this. Okay, so let's go over an example to see how this course works. So here we have the tabby cat scratch the couch, and imagine we have put the number above each one of them, where this number is the position at which this word appears in. So when we have created our dependency parse tree, another way we can record it is to have rows where in each row we have a single word, and in columns we record whether this current word is dependent, and if it's dependent, what is the head, I don't know how to say this precisely, the number of the word which is the head for this word over here. And remember, it can be dependent only once. And if there is a relationship, what is the relationship label? So imagine this is a gold standard, and now let's see some made up example about the predicted dependencies. Basically, what you are then doing is comparing this table of the gold standard dependencies with this table of predicted dependencies. And what we can see is that in the first row, this is not good, right? We have that the head is in the second word, while it's actually the third word. Then we have the issue that, here it says that the third word is the head, but we have predicted that it's fourth. But then when we compare other heads, we see that it's actually correct. We have predicted all the other heads well. And we also notice that there are some mismatches between the labels for the dependencies. So in the end, we find that 2 edges are structurally incorrect, and the unlabeled attachment score, because there are 6 possible dependencies over here, is going to be 4 out of 6, because 4 are correct out of 6 possible. So unlabeled attachment score for this single example is 66%. And then we also observe that 3 labeled edges are incorrect, and we will therefore have 3/6 for our labeled attachment score. And that's it. In this way, you are evaluating the dependency parser. Okay, so we are at time 2:45, so we'll end here. And this is as much as I want to say about syntactic structure. We are going to talk a little bit more about semantics and discourse on Monday, have our overview session on Wednesday, and that's going to be it. So have a nice Thanksgiving break. I hope you eat a lot tomorrow and then rest a lot on Friday because you ate too much. All right, I'll stick around if you need me for anything.
Thank you. Happy Thanksgiving to you too.
Thank you.
You.